So now we're going to move on to Chapter 11 and the basic energy model. Now, the way Knight describes the basic energy model is he has the system and the environment. So inside the system, all right, you can convert between kinetic potential and then thermal energies. And what happens is work is something that the environment is one of the ways the environment and the system can transfer energy. So if work is greater than 0, the environment does work on the system. If work is less than 0, the system does work on the environment. Let's talk a little bit about work and some definitions. So we're going to start with work by a constant force in the same direction as motion. So we're going to start with the simplest version of work we can. To do work, you need two things. You need a force and you need some kind of a motion. And so let's just say I lift my book upwards with a force F through a distance delta S. Okay, so the work then will be the force times that distance delta S, or the force times the displacement. In this case, and be very careful. So in this case, it only works for a constant force, and it's only true when the force is in the same direction as the displacement. Let's try an example. Here's a box. I'm pushing on the box with a force of 25 newtons through a distance of 35 meters. How much work do I do? Well, due to this new equation we have, you just basically take the force times the distance, and you get 875 joules. Now, this is not too bad as far as difficulty. Just be careful, because probably 50% of our work examples will be like this. Okay, they'll be simpler like this, and it's very easy to make it seem more complicated than it really is. Okay. So now let's look at one that's a little bit more complicated. So here's the same situation, but I've moved my force up at an angle of 30 degrees. So look at this one over, give it a try, and we'll talk about this one in a few seconds. Okay, so in this case here, you can think about your force as having two components. There's one component in the x direction, one component in the y direction. The way we kind of think about this is that only the component in the x direction does work. All right, this component of the force is actually what's making the box move. This part over here is essentially wasted, you can think about it as. And so the answer I get is 760. And so to do this, F cosine 30 would be my component of force in the direction of the displacement, which I get 21.65 for that number when I figured that out. And then essentially I just take that force times the distance, so the force that's actually helping the motion, and I get about 760 joules. And so this gives us a more general definition of work. F cosine theta times the displacement. So F is the magnitude of the force, delta S is the displacement, and theta is the angle between the two. So this works for forces that aren't exactly in the same direction of motion. Let's look at a different example. Okay, so let's say we have another problem. So in this problem, say there's some force over here that's pressing on this box and moves this box a distance of 20 meters. My question is, how much work does the normal force do? Well, hopefully it makes sense that the normal force doesn't do any work. It's exactly 90 degrees to the motion, and so it doesn't do any work. We can actually test that with our new equation, okay, because we know that the normal force and the displacement are 90 degrees apart. If we plug in cosine of 90, we get 0. But also, more fundamentally, the way I like to think about it is the force either helps, hinders, or does nothing for the motion. So this force F is helping the motion. It's moving it in the direction of the motion. Say if there was some force, maybe I'll call it force of friction, moving backwards, that would be hindering the motion, whereas the normal force does neither, just is sort of along for the ride. All right, so you can figure this out with your equation or conceptually, either way, as long as one of these ways makes sense to you. Some interesting things about work. You have to move the object to do work. The classic example is if I'm holding up a dumbbell, but the dumbbell doesn't move. I do no work on the dumbbell. All right, so you gotta be real careful about that. That's the definition of work. So in physics, we define things a little bit differently than you might think about it in the everyday world. But the definition, in order to do work on an object, you have to move the object through some distance. All right, and then, so if force is perpendicular, it does no work. That can be kind of tricky. There'll be some examples that will show that will kind of test you on that one. But you can have positive or negative work. And basically, positive is if you're helping the motion, negative is if you're hindering the motion. And finally, work is a scalar, which means it's easier for us to use than a vector. So positive versus negative work, if part of your force points in the same direction as the displacement, work is positive. If part of it works in the other direction, the work is negative. And then if it's neither, it would be 0 work. Okay, so just a good example is friction will oftentimes do negative work. Now, the fundamental definition of work, okay, so we've talked about sort of the simple cases where it's a constant force, but the fundamental case when your force isn't constant is the work is the integral of F ds. And again, for our purposes here in Physics 131, what this means is if we have an F versus S curve, okay, like this, so it's not some force that's not constant, then basically the work is simply the area under the curve. We'll talk a little bit about this later. That's what it would be for us right now. That's essentially what this means to us. And so this is a case where the force is allowed to change. If the force is constant, we use the equations we've been using so far. The last thing before we move on to a kind of a little different topic about work is just this definition of the total work. The total work on some object is the sum, and so here you're adding up a whole bunch, is the sum of all the works by all the forces acting on them. Okay. Another way to think about it is the work total is the work done by the net force. So we could also kind of write this out here as it's the work of the net force. So the net force times the displacement delta S. So you can think about it kind of either way. And so let's look at an example here. A block is pulled by a force of 400 newtons, as in the picture, which means it's at an angle of 20, and there's a frictional force that opposes this at a force of 200 newtons. I want you guys to stop now, pause this, and figure out what is the total work done. Okay, when I did this, I got 3517 joules. Let's look at this. So here's the picture. So the work total is the sum of all the work done. Now the two forces doing work are the force of the pull and the force of friction. Now also there would have to be this normal force and an mg, but again they're at 90 degrees, so they don't do any work. They're just kind of along for the ride. And so the work of the friction, here would be my equation. Now technically you could write in here that the angle is 180 degrees. And that'll give you a negative sign. Now you can do that. I like to just remember in my head that it has to be a negative sign because the friction is hindering the motion, right? The motion is this way, friction is hindering it, negative work. The force of the pull is helping it, positive work. But as long as one way works for you. The force of the pull is the same equation, so it's 400 newtons, and this is the angle between them is 20, and the distance is 20 meters, so I get 7517. And then the total work is simply just adding the two numbers up to get an answer of 3517. Now, we're going to use this for a new theorem that we have, and so we're going to go through and calculate this theorem. So suppose I apply constant force along the x-axis to a point on particle m. And so the work would be this force I'm applying times the delta x that it travels through. Now we can go back to Newton's laws, and for x we can write that as the mass times the acceleration. Now we had these equations, kinematic equations, okay, and one of them looked kind of like this here. If I solve it just for a times delta x, I get 1/2 the difference in the velocities. So for over here, I can replace this part here as 1/2 the difference in the velocities. And so I brought the 1/2 out front, the difference in the velocities, and here's the mass. And so I have this equation that says that the work done is equal to what this over here you can think of as being the difference in the kinetic energies. And so what this theorem says is that if I apply work on something, I'm going to change the kinetic energy of something else. And so this theorem can be written here in a shorthand. Work equals the change in the kinetic energy. Let's apply this and see how this works. So here's our equation written out. The work total, again, the sum of all the works equals the final kinetic energy minus the initial kinetic energy. So if positive work is put into the object, so the total work is positive, the velocity will increase, the speed increases. If negative work, if the work total is negative, its speed decreases. And how you find out exactly how much it increases or decreases with this equation over here. Now, one thing just to be real careful of is we're interested in all the work, the work of all the different forces. So make sure that you find all the forces. That's probably the biggest thing that can go wrong with this guy. And so here's the same setup from last time, the same forces. If you're pushing this block, I want to know is if the mass of the block is 100 kilograms, what is its final velocity? Go ahead, pause, give us a try, and we'll talk about it. Okay, so with this case here, this is a little bit easier because we already calculated the work. In the last example, it was 3517 joules. And so basically, I set up this equation right here. I know the mass is 100 kilograms, and the work total is 3517. And so we are told that the block starts at rest, and so I can go through and solve for the final velocity. So if I get rid of, so basically the initial part goes away. I'm left with this here. Basically I can solve this like so. And at the end, I come out and if I plug everything in, I get 8.38 meters per second.